These are graphene-reinforced PLA and PETG. Theoretically they should reduce the wearing and the friction, but what about mechanical properties? Let's find out. Welcome back to my tech farm. Another material testing video, this time PLA and PETG. These are graphene strong filaments by Prografen. And I bought these filaments myself, but not directly from the company. Somehow their phone don't exist, they don't answer to emails, so I didn't dare to buy from their website. I bought it from the reseller. This was the Patreon request, and I was also very curious about these materials. And exactly for this kind of purposes, I have the budget from the Polymaker, who will soon become a channel sponsor. And don't worry, they don't have any kind of the effect to my results, they are just sponsoring my research. In the meantime, they changed the website. Now it is only in Polish language. On web archive we can see the old version of the website, which was in English too. Let's see some specifications from this old website. The addition of graphene increases the stiffness and tensile strength of the filament, and both are parts of my regular testing methods, and I will include here some data of the average PLA and PETG filament for the better comparison. Two more information from the website, and they are valid for both filaments. Printed parts have higher abrasion resistance, and they feature a very good friction coefficient of printed parts. This means I have to figure out another test for the friction and wearing of these materials. About print settings, we have quite big difference between informations given on the website and these on these stickers. This makes most sense to me. Here you can see on the upper part of the screen, which I collected from the website informations, and on the bottom part you can see the stickers. About printing speeds, of course PETG have a lower maximal recommended print speed of 150 mm per second versus PLA, which has a 300 mm per second maximal speed. Plastic spool vacuum packaging and same information on the sticker like on the box. The bags are resealable. Both are in black color. Let's see how brittle are these filaments. This is PLA. And it's not brittle until it's new. Probably by time it will become more brittle. And now let's see the PETG. Yes, I can even bend it. About recommended nozzle type. I checked from 3 different sources, even with the resellers, and all of them mentioned that it can be used with a regular brass nozzle. We don't need a hardened steel or similar wear-resistant nozzle type. The printing will be on Babylab A1. It has a stock stainless steel nozzle, and I'm starting with the PLA Strong. This is still the first layer. The start is completely okay. The progress is good. The printing is at 50% and it has a really nice matte surface, but I will analyze this later. And the last few vertically printed test objects. Just for curiosity, the bed adhesion check until it's hot. Okay. These are some additional test objects for the friction and wearing test. It's time to move to the PETG. It was in a dryer few hours. PETG is loaded too, and this start also looks very nice and clean. The printing is at 30% and it's completely fine so far. It's finished, I wasn't even here. The bed cooled down to 45 degrees Celsius. And PETG test objects for the friction and wearing test. And now everything is printed. Adhesion friction on the glass. These legs are 3D printed. And I'm starting with the PLA. Total load is 3.5 kilograms. The big average is 0.27 kilograms.
0.26.
And now PETG.
0.23.
And the average value is 0.23. This means less friction with the PETG compared to the PLA.
0.23.
And now let's measure the sliding friction. The speed is not big, only 2 meters per minute, but it is still a sliding friction. PLA 0.54 approximately. And the PETG 0.5 kilograms. Again less friction with the PETG. Just another quick proof that PETG has a smaller friction. Here they go together, but in this direction PETG will start sliding earlier. This is from old video. The regular PETG has a bigger static friction on the glass, but the same regular PETG has a smaller sliding friction on aluminum compared to the graphene filaments. So now we have one more very accurate friction test, only I couldn't finish the programming for this video, but test objects are printed and I will test these graphene-reinforced filaments in presenting video of this machine. The wiring test, and I'm starting with PLA. The shaft is 3 mm in diameter and the load will be 2.5 kilograms. And there will be 200 repeats. Okay, for the first look, this wiring looks small, but I will measure it later. And this is PETG. It's time to measure the depth of the groove. This is PLA. 0.18 millimeters. And now PETG. Similar 0.18 millimeters, and these are very good values actually. For average PETG, this depth would be approximately 0.5 millimeters. The tensile test with horizontally printed test objects. Smallest cross-section area is 4 by 4 millimeters. As I mentioned, I will include here the values for the average PLA and PETG. This is calculated from more than 20 tested materials, and we can see in both cases the graphene-reinforced filaments were weaker, and compared to each other, the tensile strength is very similar. And now the layer adhesion. The previous was 40 and 44, the PLA layer adhesion, I didn't record it. I just couldn't leave it like this, so I reprinted the test objects, and this is recorded next day. Back to original timeline, this is PETG. According to my rating, the graphene-reinforced PLA has a great layer adhesion, very similar to the average PLA, but this graphene-reinforced PETG is very weak, and also very far from the average PETG. And a reminder, I was already printing here on the maximum recommended print temperature. Shear test, objects printed in horizontal position. Printed vertically where the layer adhesion is important. Horizontally printed more or less similar to the non-reinforced versions. Vertically printed objects, only graphene-reinforced PLA looks stronger, others are very similar, but here I have quite big inaccuracy because I started this testing later and I have only 5 or 6 objects in this average value. The torsion or twist test, and I'm starting with horizontal printed ones. 1.1, 1.7, oops, 1.1, 1.8, and now vertically printed 1.6. Interesting, PETG was less flexible in this case, but let's analyze the numbers. Horizontally printed, the graphene-reinforced filaments are stronger compared to the base average materials. Vertically printed, the PLA is far the strongest, and probably we have the similar ratio here. The graphene-reinforced PETG would be even better if it would have a better layer adhesion. Eyes impact test with this half kilogram hammer. This is PLA. 0 position. PETG. By the way, who can recognize my new toy? 0 position of the hammer. Edge position after breaking PLA and after PETG. PLA is tougher to the PETG, but in both cases these are quite brittle materials. There are some special tough filaments which will deform this average PLA value, so they are excluded here. 3-point bending test. With these loads which will be placed one by one, and I will measure the deformation after 1, 30 and 60 seconds. Deformation under 1.25 kilograms. Under 2.5 kilograms, 5 kilograms, still very minimal additional deformation during the time, and this is under 10 kilograms. No permanent deformation on them after this test. In both cases, PLA is stronger than PETG, but also in both cases the graphene reinforcing helps against the bending and also against the additional deformation during this 1 minute. So yes, this is one of those cases where you like to use the graphene reinforcing against the regular materials. The creep tests the deformation under constant load, and I have several tests in the progress, this time all black filaments, PPS-CF, PHT-CF, graphene-reinforced PLA, and graphene-reinforced PETG. The load is 1.25 kilograms. Interesting, surprisingly small star deformation on these two. 14.78, 16.14. They will be measured every day, but in the video let's jump in the time. This is day 5, time for the last measuring. 16.15, 16.81. Looks like this PETG almost completely stopped with the creeping. Still has bigger deformation than the PLA, but if I would continue this test maybe one more week, I'm quite sure that here on the PLA the deformation would be bigger compared to the PETG. I'm not sure is it visible on the screen too, but definitely I can see more permanent deformation on the PLA compared to the PETG. On this graph we can see the distance between two reference surfaces. On the other we can see the difference between 2 days, that's the creeping. And we can see less deformation on the graphene-reinforced PLA compared to the PETG, but more deformation during these 5 days. This means more creeping. But if we compare it with these regular average PLA and PETG materials, we can see definitely another advantage of these graphene-reinforced filaments because they have significantly less creeping. For the average materials, I'm recording only first 2 days in the summary table from my pattern supporters. Temperature test in the oven, and 2 on the right side are graphene filaments. This is PLA and PETG. This is time-lapse video, and the first deformation I could record on the PLA, and shortly after this on PETG, and I was running this test much longer because of that PBT test object here, and of course this was too much for these PLA and PETG materials. But in both cases they are very close to the average values for their own material type. Quick summary of our results without any additional comments. Results for the tensile test, layer adhesion, shear test, bending deformation after 30 seconds, bending all results, torque or twist test, impact test, and the temperature test. I have the feeling that I'm still missing some kind of test where all these tribal filaments will start to shine. Maybe some bigger load, longer test, bigger speeds or something like that. Because yes, here for example I can measure some improvement, but I wouldn't say that it is significant improvement compared to the regular, I don't know, PETG or PLA. About its mechanical properties, yes, this graphene-reinforced improved the stiffness and rigidity of the filament, but on the other side, especially with the PETG, the layer adhesion is very weak. Yes, we can improve this by printing on much higher temperatures, for example on 270 to 80 degrees Celsius, we can go this high with the PETG if the printability is okay. Of course, these are not carbon fibers. I'm not sure if graphene reinforcing helps with the printability. The parts look still nice, but with this we can move to maybe acceptable layer adhesion, so this is still not good enough for me. Small gift for those who is still watching the video. So I tried with PETG on 275 degrees Celsius, and the result is quite a lot of stringing, so even if you try this, definitely it should be very dry. But let's see the layer adhesion. I have 4 test objects and you can see very disappointing. Not really what I expected. Looks like some PETG materials, or maybe this graphene start to degrade on these temperatures above 270-275 degrees Celsius. So the conclusion, don't go too much higher above the recommended print temperatures given by manufacturer. And again, huge thanks to all my pattern supporters, because with their donations and together with the budget which I got from the polymaker, I can buy any filament I want to test, and I have this freedom. I don't have to wait for the companies if they want to send me the filament for the testing or not. Thank you for watching this video and happy printing!